Process right away in chapter 20 is specific heat, heat of fusion, heat of vaporization. Okay, so we'll do a couple. That topic is not too hard, and I'm sure you've seen it in chemistry quite a bit. Specific heat, capacity, heat of fusion, heat of vaporization. Okay, so let's go back to the heat of specific heat. Heat capacity or thermal capacity is a physical quantity equal to the ratio of the heat that is added or removed from an object to the resulting change in temperature. So, right, it's, you say H is equal to mc delta T. In actuality, it's actually a derivative equation. dH is equal to mc dt, so C is equal to the derivative of H with respect to T, 1 over m, right? But in most cases, we're assuming that the specific heat of the material is constant over as a function of temperature. So if the specific heat is constant, then this equation changes into a delta equation, right? So then you just write it as H is mc delta T. Okay, for liquids, we're going to use this equation. Liquids and solids. Liquids and solids. When we get to chapter, I think it's 22 or 21, I forgot which of them, 21 or 22, then we're going to define the specific heat of a gas, but instead of using mass, we're going to use number of moles of the gas, not the mass of the gas. So then we're going to have 1 over n dH dt, but we're going to have two specific heats. One is specific heat at constant pressure, the other one is specific heat at constant volume. So for gas, it depends how are you heating it, right? Are you heating it while holding the volume constant or while holding the pressure constant? Isobaric, isovolume. So then you have specific heat at constant pressure, constant volume. Here, since solids don't expand that much compared to gases, the process by which you're heating it doesn't matter. They do expand, but not as much as gases do. You know, so C is 1 over H dH dt. The process doesn't matter. The constant pressure, constant volume. And for solids and liquids, their masses matter more than the number of moles. You know, whereas gases, it's 1 over n. So for solids and liquids, what's the units of specific heat? Joules per kilogram per Celsius, right? It's going to be joules, which is the specific heat J, the heat, and this is going to be kilogram Celsius. Or you can do joules per gram Celsius, or you could do what else? What's another unit of heat? Calories per gram Celsius, or you can do what? Food calories per gram Celsius. For gases, it's going to be similar, except instead of kilogram, gram, it's going to be moles, right? So you can do joules per mole Celsius, or, well, you don't have these two versions anymore because mole is a mole, or you could do calories per mole Celsius, or little calories per mole Celsius, or you can do big calories per mole Celsius. Big calories is the food calories. So let's look at a table maybe. You see here, definition. The heat capacity of an object usually denoted as C is the limit dq dt as delta Q goes to 0. In other words, if I put an infinitesimal amount of heat, how much does the temperature go up by, right? And the resulting change in temperature. Where delta Q is an amount of heat added to the object, and delta T is the resulting increase in temperature. Now, why did they define it that way? Couldn't they have defined it as delta T over delta Q? Because usually when you take a limit as dq goes to 0, shouldn't dq be on the bottom? The answer is, it's just a matter of preference. They could have defined C as dq dt, and then the equation would have been written opposite. It would have been written H is m delta T over C. Perfectly fine, but then our numbers would have changed. The units of the C would have been kilograms Celsius over joules. Everything would be inverted, and then we would make a whole table of what's the specific heat of water, right? But the meaning of it would also slightly change, because right now, if the specific heat of a substance is large, what does that mean? Is it easy to heat or hard to heat if it's large? Well, with the way we've defined it, if the specific heat is large, for a given heat input, the change in temperature is low, right? For a given amount of heat input, it doesn't change its temperature. So if the specific heat is high, that means it's hard to heat that substance. If we had defined it this way, it would be opposite. If the specific heat is high, it would be easy to heat it, right? So sometimes it's a matter of convention, why we defined it that way. Sometimes there's a historical reason. For whatever reason, it's defined like that. And then they talk about the specific heat capacity, molar specific heat, which is for gases, right? 1 over n, see here, number of moles. Volumetric heat capacity, alternatives unit systems, calories, measurement. Let's see if there's a table. Then it gets a bit complicated. It goes into all the differential equations, and this is what upper division will do a lot of this. This is they're applying the first law of thermodynamics. CV is du, dq, dt with B held constant. Then they introduce Gibbs free energy and entropy, right? Oh, so good, huh? Just even scrolling over it makes your juices, your mouth water. Oh, yeah. Polytropic heat capacity. Heat capacity at absolute zero. Negative heat capacity. Oh, that's weird. That means negative would mean if you put in heat, it actually gets colder. Huh, that's weird. Most physical systems exhibit positive. However, even though it can be seen paradoxical, there are some systems for which the heat capacity is negative. These are inhomogeneous systems that do not meet the strict definition of thermodynamic equilibrium. They include gravitating objects such as stars and galaxies, and also sometimes some nanoscale clusters of a few tens of atoms, close to a phase transition. A negative heat capacity can result in a negative temperature. Wow. according to the Virial Theorem, for a self-gravitating body like a star or an interstellar gas cloud, average potential energy and the average kinetic energy are locked together in the relation U potential is negative 2. That one actually we've seen it when we did gravity. Remember we saw gravity is gmm over 2r, and the potential energy is negative gmm over r. It's twice the kinetic energy. So the total energy therefore obeys U is negative U kinetic. A more extreme version of this occurs with black holes. According to black hole thermodynamics, the more mass and energy a black hole absorbs, the colder it becomes. Right? So that means over time, the bigger the surface area, it is cooler. Black hole thermal, the more mass and energy a black hole absorbs, the colder it becomes. In contrast, if it is a net emitter of energy through Hawking radiation, it will become hotter and hotter until it boils away. Okay, so black holes have what's known as temperature, and that's why they do Hawking radiation. They emit radiation, and eventually they're going to boil away. The small ones boil away a lot quicker because they're hotter. Okay, so it's almost like the black holes have that negative specific heat. Interesting stuff, huh? Introduces so many cool topics. Okay, so later we're going to look at specific heats of monatomic gases, diatomic gases when we get to chapter 21 and 21, I believe. So now let's look at the solids. In this table, they're kind of putting them all together, air, aluminum, and then they're giving you the isobaric mass heat capacity, isobaric volumetric heat capacity. So for example, aluminum, they're giving you the heat capacity joules per gram per Kelvin. Well, why did they give Kelvin and not Celsius? Why are they calling it Kelvin? Well, is this equation one that cares if it's Kelvin or Celsius? It's based on delta T, right? So can delta T be Kelvin or Celsius? Yes. A unit change of Kelvin is the same as unit change of Celsius. So is it wrong for me to call this Kelvin? No. I can call it Kelvin or Celsius. I don't care. You see? So the first one for aluminum is 0.897. So which one are they giving you? The specific heat of aluminum, 0.897, and then they're giving you joules per gram per Celsius, let's call it. Joules per gram. So they're giving you this one. This one, joules per gram Celsius, right? And then the other one they're giving you is the joules per mole per Celsius. That's weird. Usually for solids we don't do moles, but they're giving it to you just in case. In other words, they're giving it to you to show that it doesn't matter if it's a solid, you can still do the moles, right? So then you can do, how would you convert that? How many grams are in 1 mole of aluminum?
37.
M over M.
You have to look at the molar mass of aluminum. The atomic weight of aluminum is 26.98. 26.98 grams per mole, right? So 1 mole of aluminum weighs 26.98 grams. .98 times 0.897, what is that going to give you? 24.2. Joules per mole per Celsius. Are we going to use that? Not too often, because for solids we don't do that. So notice they're calling this isobaric mass heat capacity. So in other words, when you heat up a solid, its temperature is going to change, its volume is going to change, so you can't really hold the volume constant for solids, right? Its volume is going to increase when you heat it. So the default is that it's an isobaric, but we don't necessarily put that CT. It's understood that solids and liquids is isobaric. Let's see. So that's CT. Okay, how about the next one? Like let's say ammonia liquid, 4.7. Joules per gram per Celsius. So of course liquid is generally going to be more than a solid, right? Oh no, hold on. Why did I say it's going to be more? Oh, I was thinking of the alpha back in chapter 19. How about for specific heat? Should the liquid be more than a solid or less? Should it be, remember more means it's harder to heat it. Should it be harder to heat up a liquid than a solid? Yeah, because when you pour in heat into the liquid, a lot of the motion goes into changing the volume of the liquid, right? The liquids increase their volume more. With a solid, it doesn't increase, so most of the heat you put in probably goes into increasing its temperature in the motion.
Like evaporate, also increases its.
Yeah, it kind of. So what I'm trying to say is that liquids in general should have a bigger, not only a bigger alpha, but a bigger beta, right? So they should expand more, but they should also have a bigger specific heat C, right? Because when you pour in heat, since their volume increases, most of the heat you pour in doesn't go into increasing their agitation. It goes into them expanding more. With a solid, you pour in heat, it doesn't increase its length too much, so most of the heat you pour in goes into the agitation of the molecules. So their alpha is smaller for solids. I mean, sorry, not the alpha, the C. And their alpha is also smaller, so they're kind of related. Ah, you see that? So we should see a pattern like for solids, it should be less, solid 0.3, solid 1.8. Copper 0.38. Now if we go to another liquid, let's go to another liquid like gasoline. You see 2.22. Gasoline is 2.22, 2.44 ethanol. Yeah, you see, so they are larger than the solids. Perfect answer. Yeah. I overheard it, yeah. So yeah, when you, with the liquid, more of the heat you put in is going into their expansion, right? And therefore, less of the heat going to increasing their agitation. Exactly. Right. So now, if we look at the metals in particular, is going to be very low. That means since they're good conductors of electricity, they also are good conductors of heat, and all the heat you put into them goes immediately into their agitation, so they warm up a lot. I've always done the mistake of going into a sauna with my chain on, you know. Never do that. You find out the hard way. You should not be there with a gold or silver or any chain. Before you know it, your chest is burning, right? So never, ever go there with glass, metal, you know. So let's see, water. Water is beautiful because water has one of the highest specific heats. Well, ammonia was actually pretty high too. Water is 4.1813, and that's also one of the reasons why life exists, right? Remember the other day I said the other reason is that the densest water is 4 degrees Celsius water. That's important for life to exist. This is also important because water, since it's very hard to heat up and cool down, right? So water acts as a buffer so that the temperature of the atmosphere doesn't change too much, you know? And then it's hard for water to freeze over, right? So it retains its temperature. So specific heat of water, 4.1813. And its specific heat seems like it is kind of constant, right? 4.1813. But water at 100 degrees, so once it turns into steam, once it completely turns into steam, it's now actually easier to warm it up, right? Because gas,
It's more active than liquids, and it's easier to.
the same argument I used why liquids are more specific heat, higher specific heat than solids. I said most of the heat you put into liquids goes into them expanding, so they're harder to heat than a solid. But now I can't use that argument for a gas and liquid. That argument fails, right? So for a gas, the heat that you put in, they increase their volume even more, right?
That's right.
So that means it should be harder to heat up a gas than a liquid. Then why is the specific heat of steam less than the water? So these things get complicated. You can't always have an easy answer for things, right? So steam is, and maybe there might be a particular quality of water which is unique to water, you know? So 2.808 joules per gram per Celsius. And then ice, in other words, solid ice, 2.05. So solid ice and steam are very close to each other. That's really weird, you know? And then the liquid is the one that's really hard. Now, all of these we can also convert to what? The other common units are calories per gram Celsius. So how do we convert from joule to calorie? We should get used to that too. They didn't give the calorie one here, but we can go to another page. Look, conversion between calories and joules. Okay, 1 kilocalorie is 4,184. So a kilocalorie is the same as a food calorie, which we call with a big C, right? So 1 food calorie is 4,184 joules, right? Or a small calorie would be 4.184 joules. So 1 small calorie, 4.184 joule. 1 food calorie, 4,184 joule. So if I want to convert this to small calories, what do I do? 4.184 joule is 1 small calorie. So I divide all of this by 4.184. 4.184 joule per 1 calorie. So what's this going to be? The specific heat of water. It should come out to be 1, right? 1 calorie per gram, but it's not exactly 1, huh?
A little less.
It's a little bit less. But the one that's usually used is just 1. They probably round it. 1 calorie per gram Celsius. If you divide this by 4.184, I think it comes out to be about half. Okay, 0.497. So steam is 0.497, which we could round to 0.5, and this is almost going to be 0.52. 35.5 calories per gram. So steam and ice are both 0.5, whereas water is 1. Those are kind of rounded numbers, but they're, for most purposes, they're good enough. Okay? So if you ever are given one of these and you want to convert to calories, just remember this conversion. Okay? How about heat of vaporization and fusion? Heat of fusion is, and there's one for boiling too. This is how much heat it takes to transition from liquid to gas, and then this one is how much heat it takes to transition from solid to liquid, or back from liquid to solid. So the enthalpy of fusion, also known as latent heat of fusion, is the change in its enthalpy resulting from providing energy, typically heat, to a specific quantity of the substance at constant pressure. So it's, again, with the pressure being held constant. For example, we're melting 1 kilogram of ice at 0 degrees Celsius under a wide range of pressures. 335.55 kilojoules of energy is absorbed with no temperature change. The heat of solidification is equal and opposite. Okay? So it's the same when you go back from liquid to solid. Okay? And it makes sense that the heat of vaporization should be more, right? The boiling not only the boiling temperature is more, but it takes more heat to actually boil it than to melt it. See, so that's different than saying the boiling temperature is higher than the freezing temperature. In other words, the heat actually required to boil is harder, because when you're going from liquid to a gas, you have to kind of break the bonding of the atoms so they can be more or less free from each other. And now they can expand even more, right? So what are some numbers there? Water, that's going to be our basic one. Specific, this is the heat of fusion of water, H2O. So it's going to be 79.72 calories per gram. And then once we write that, we don't have to write the other one because we just know the conversion. You know, 1 calorie is 4.184. The other one's methane, glycerol. So it does look like water is also high in that compared to other ones. You know, so its specific heat is high, and also heat of fusion is high. The other ones are like 13, 19, 45, 23, 47. Yeah, I don't see one here, at least in this list, I don't see one that's higher than water, right? So there's some trend there. So it's hard to break the bonding of water, and it's also hard to agitate water to heat it, you see? Okay, there's also some calculus, partial derivatives. Now let's look at the heat of vaporization. You see that the usual plots that they put here. This is the amount of heat that you have to put in, but the change in temperature is 0, right? So the amount of heat required to melt it is a lot less than the required heat to boil it.